Hello, I am going to talk about the naming of alkenes with respect to isomerism. Now, we already know how to use the cis and trans notation based on the alignment of similar groups across the double bond. So if we have similar groups, like in this case methyl groups on the same side, we use the cis. If you have those methyl groups on opposite sides, we use the trans. The next thing I want us to consider is how to use the E and Z configurations. Now here, we are going to look at the sp2 hybridized carbons, and then we are going to assign priorities to the substituents on those carbons. Okay, so we can start from the one on the right. The high priority is that one, and then the one on the left, the high priority is fluorine in terms of the atomic numbers. If the highest priority groups are on the same side, we use Z configuration. If the highest priority groups are on different sides, we use E configuration. So notice in this case, these priority groups are not similar, so we cannot use trans or cis. Okay? Let us see how we can apply that in the naming of alkenes. So, in the naming of alkenes, we follow the systematic rules similar to the ones that we learned in the naming of alkanes. The only difference is we have to consider the functional group, the alkene, within the parent structure. So here, let us start with the first one here. What we are going to do is to look at the way by which we can name it, so we have the lowest numerical value for the substituent, and we have to start with the longest chain that contains the functional group. So we can do 1, 2, 3. Okay, so that gives us the lowest value. So we have methyl cyclohexene. And then we have to determine the stereochemistry at that position, which is going to be an R. So we have R3-methyl cyclohexene. If there's only one stereo center, you don't have to bother about putting 3R or anything like that. But if there's more than one stereo center, like in this case, let us consider here, we are going to have 1, 2, 3, 4, 5, 6, 7. And that is because the longest chain that contains the functional group is the one we start with, and by giving it position 2, we are going to have the lowest numerical value. So that's going to be 2-heptene as the parent name, 2-heptene. Okay? Then we look at the substituents. So here we have bromo, we also have an ethyl group, but those ones have stereo centers. So we need to assign the stereo centers accordingly. So here, the position 4 is going to have an R configuration. So we write 4R. Position 6 has an S configuration, so we write 6S. If we have E or Z configuration, that one comes first before the R or S configuration. So like in this case, it was 2-heptene. Then we need to look at the priority groups that are attached to the double bond. So here we have the highest priorities on the opposite sides. So that's going to be an E configuration. But there's only one double bond, so we don't have to worry about writing 2E or 3E. In this case it's 2E, but we don't have to put 2 because there's only one alkene group. So we're going to call that E, 4R, 6S, 6-bromo, 4-ethyl, 2-heptene. Okay? Let us look at another case. How do we name this compound? Remember, always we need to start from the most substituted carbon that contains the functional group. So in this case, we have to start from here, number 1. And our alkene is going clockwise, so number 2, 3, 4, 5, and 6. So this is going to be 6-chloro, 1-methyl cyclohexene. Remember here we did not say 1-hexene. Whenever you have a ring, we don't say 1-hexene, we just say cyclohexene. Cyclohexene, because the position where the functional group is assumed to be position 1, so we don't have to say 1 unless there was another double bond, then we would include another position. Okay, so we end up with S, 6-chloro. Notice here, again we used S because there's only one stereocenter. We don't have to say 6S. Okay. The other common names we need to know is ethylene, propylene, and styrene, because we will use these ones again in some of the upcoming chapters. In terms of the stability, we can be able to predict the stability of an alkene just by looking at the structure. Now, usually, if we are looking at the relative stability of alkenes, we need to compare their heats of combustion. For example, the trans alkene is 4 kilojoules per mole more stable than the cis alkene, which means that the cis alkene will produce more energy during an exothermic reaction. When you carry out combustion, it's going to produce more energy than the transalkene. Compounds that are stable are less reactive. Okay, so we can use this to determine the stability. And from these values, we can also determine the stability of the ones that are more substituted and the ones that are less substituted. So, more substituted alkenes are relatively stable compared to the less substituted alkenes. So by looking at the structure, we can be able to predict the stability of an alkene. For cyclic alkenes with less than 7 carbon atoms in the ring, only the cis alkenes are stable. So you do not have to indicate cis or trans. You just draw the cis structure. Okay? Now, when it comes to bridged bicycloalkenes, this rule of 7 carbon atoms is referred to Brett's rule. So if you have less than 7 carbon atoms in a bicycloalkene, then it's not possible to have a double bond on a bridgehead. Okay? If we have 8 or more, then it's okay to have a double bond on a bridgehead because this is less strained. Otherwise, if you have like 6 members, then it's possible to have a carbon double bond on positions other than a bridgehead. If you want to verify this, I encourage you to use the molecular model to develop the structures and see how possible or how impossible it is to form these compounds.